And so, issue 313's puzzle, what does it say? This week's puzzle. The prime number 3511 is pretty special. More on that after. Since 2 to the power 3511 minus 1, take away 1 is divisible by 3511 squared. Can you find another prime which satisfies the same condition? 2 to the power p minus 1 subtract 1 is divisible by p squared. And then that little note, that number 3511 is also an IMIRP, because, since that says prime backwards, that number is also a prime number when written backwards. Well, what have we got here for this puzzle? A piece of skullduggery is what we've got here, because, quite frankly, you're not going to be able to do this. Not without writing some computer program. So, strictly speaking, this isn't a puzzle, as in something you can just do with pencil and paper. Not even a calculator, strictly speaking, if it's to be a puzzle. If you got the answer to this, the overwhelming probability is you just Googled the problem. You Googled the problem, and up came this thing here, and up came the answer that you required. Up came a thing, and it said, and it mentioned Wieferich, German name, prime, or primes, and it probably mentioned the numbers 1093, and 3511, since they're the only two known ones that satisfies the ones base 2 known so far, despite enormous searches by the world's most powerful computers running the most exotic algorithms. He didn't find that. It was someone later on that found this first one that satisfied that equation, because it requires an enormous amount of arithmetic. So given that you didn't search through all the primes till you found one that worked, till you found that one, you might have suspected some skullduggery in that previous issues of puzzles have had the issue number or the subscriber number as a solution. So you might think, right, that must mean it's either 313 or 1093. Issue 313, 1093 subscribers. It's one of them that works. Then you'll say, I'll just check which one it is by dividing. So you try that, and you switch on your calculator and say 2 to the power, remember 1 off, 312, take away 1, ooh, and you've got a 94-digit whole number. Does that divide by 313 squared? Divided by 313 squared is, I've got an 89-digit whole number part, because it's in standard form. Is that or is that not a whole number? That says the point's 88 places forward, but it doesn't tell me whether there are any succeeding or following decimal places. I've got no idea if that divides in exactly. And if I try it with this one, the whole thing packs in, because this has only got a capacity of 100 digits altogether. So I can't even test them. Maybe if you had some function like the int function that would extract the integral part of it, but I don't think I've got that in this calculator. Which means I can't even test which ones of those might be divisible, might work. Now what follows is just an enormous amount of arithmetic. There are ways of doing it. And that way is to use the remainders, is to use modulo arithmetic. If that's divisible, I'll just go to the number 313. If 2 to the power 313 minus 1 is divisible, it means it's congruent to 0 mod 313 squared. Or better than that, 2 to the power 312 is congruent to 1. I want a remainder of 1 when I do that. Now I can't get that straight away from the end because it was just too big for the calculator, but you can work your way up to it. There is a way of doing it by hand, but you'd have to work your way through it. You'd have to start with some power of 2 that might be accessible. Well, 313 squared is 97969. So there's no point trying them until I exceed that. So I want to get, if that's 2 to the power 10 is 1064, that's a 6, so probably 2 to the power 17 is what I'd start with. What's 2 to the power 17 congruent to? Well, you could work it out yourself, I'll just do that quickly. Is 131072. That's greater than that, so you can take one of them away. So minus 97969 equals 33103. This is all mod this. So that starts the ball rolling. Now all you need to do to get the rest is step up through the powers. Go up to power 18. That would be doubling it, so double that number. Doubling that number is 66206. And if it exceeds that, subtract it. If not, that's the remainder, that's the residue. Go on to the next number, 2 to the power 19. Double it. If that exceeds it, subtract it. Then go on to the next number. So by hand, you can double and subtract this quite easily. Well, not quite easily, but you can do that without a calculator. And eventually, by the end of the day, you'd have reached 2 to the power 312. And if the final remainder was in fact 1, then 313 would work. So it is possible, but that would take an awful lot of time. Now, there's a quicker way to check 2 to the 312 to see if it's congruent to 1 mod 313 squared. And that's to break this down into powers of 2. So 2 to the 312, what would be the binary representation of that? Well, the highest power of 2 that I can get in there is 256. So take out 256, I'll put it over here. 312, take away 256. I'm just doing this rather than starting with 312 and then do a big long divide by 2 all the time and noting the remainders. Take away 256 is 56. Biggest power I can get there is 32, so 2 to the power 32 for a power of 2. Take away 32, I'm down to 24. I can get a 16 out of that, and a 16 leaves an 8. What I can do here is, to find the remainder here, I can find the remainders for these 4 and multiply them together, and then reduce it again, mod 313 squared. So it's just a case of starting with, just a case. That's what I mean, you didn't do this yourself here. 2 to the power 8 is congruent to, well, 2 to the power 8 is less than that number, it's just 256, so that is the remainder. But now what you can do once you've got powers of 2 as the exponents is square these. Squaring this would double the exponent, so that would make it 2 to the 16. Squaring that, now you have to do it yourself. Squaring that, well, that's 65536. That's still under. Now step up to 32, so squaring that, now it gets big. And this is where you'd have to use a calculator in this method. I'm not going to do it all, I'll just do this line and then fill in the rest. So you'd have to do 65536, square it, get this number. Don't know if that shows. Mod 313 squared, so instead of that, divide by 97969. You get this decimal. Now, I've got the whole number part there. I could subtract that whole number part times 313 squared, or I could just subtract the whole number part and rehydrate the decimal part. But it means I'll need to remember this. 43840. 43840. Leaves me with 0 point that. Multiply that by the 97969, and hopefully it will come back to a whole number. It might not exactly, because there's only 100 spaces to hold whole numbers and decimals. The decimal part was truncated by a small amount. There, 9999993. So it must be 6336 that should have been. And then keep on doing the same thing, unless you've got a calculator with an int function. I don't know if that'd be any quicker than just dividing by the number, pulling off the whole number and multiplying the decimal part to find the remainder. And then you would carry on to 2 to the power 64 in the same way, would give you 75575. Doubling that again to 128 would give you 85894. Doubling that again to 256 would give you 27753. Once you've done the business of divide by 313 squared and then remultiply the decimal portion. And that's all we need. So that means that 2 to the 312, whatever its remainder is, should be congruent to 2 to the 256 times 2 to the 32 times 2 to the 16 times 2 to the 8. So that would be 27753 times 2 to the 32, 6336, 2 to the 16, 65536, 2 to the 8, 256. It'd be congruent to that, mod 313 squared. Type that into your calculator, and then divide by 313 squared and rehydrate the decimal part, and that would be your answer. Except you can't do that on your ordinary little handheld 100-digit calculator, because you won't see all of the whole number to be able to subtract it. You could do it on an iPad and so on, because they go to 144 digits. If that was too big for the whole number part to be clear, you'd have to split it up probably and do that product first and bring it down mod 313 squared. If you did that, that comes to 86622. That, when you multiply it and bring it down, comes to 24517. So that in the end, multiplying them and bringing it down gives you a final remainder of 37561. So when that's divided, it's got a remainder of 37561. It's not equal to 1. So after all that, I know that 313 doesn't work. Quite a palaver. So if you were doing this whole thing with a calculator, you'd have to go through all the prime numbers, trying this out until you found the first one that gave you a 1 at the end of it. So, is 1093 one of those primes? Is 2 to the power 1092, 1 less than it, congruent to 1, mod that squared? Well, using that second method there, rather than plodding through all the way, one at a time up to 1090, you could break that into a primary combination of them. So 1092, well, 1024's in that. So 1092, and then take away the 1024 rather than going through. Well, actually, maybe we'll just go through that division. See if you divide through by this. I'll just rattle it all down. Although that is less helpful, having that as a binary digit. But writing out that binary digit, you've got this. You've got 100010001000 base 2. That's what 192 base 10 is equal to. If you change that, notice there's a wee sort of pattern here. If you extend it. If you change that into base 16, then that's the 1s, 2s, 4s, that's 4, 1s, 2s, 4. 1092 is actually 444 base 16. Anyway, I didn't need that. I just want to break this down. So 1024, taking that away, is going to be 68, so that's a 64, and that leaves another 4. So it breaks into that, which means if I can find the residuals of them and multiply them together, that'll be the residual of this. So the same as before. I'll start with that 2 to the 4. So 2 to the 4 is obviously 16. 2 to the 8, same as before, is 256, and squaring both sides again takes you up to the 65536. Remember, this time it's not the mod 313 squared, it's mod this squared, which is 11,94649. So we go to 2 to the 32. To get that, you'd square that, and you arrive at this. Remember that whole process, then you square it, divide it by this, remove the whole number part, which, because you're keeping them small, is hopefully still on the screen so you can see it, rehydrate the decimal part. 2 to the 64, you can try this yourself, and keep squaring them and going through the routine. And finally 2 to the 1024. Would give you those for the residuals, and then just choose the appropriate 3. So it's this one, 917050, multiplied by 64 is this one, which is 60, that's a pretty horrible looking O, 6814, multiplied by this one, which is just 16. Multiplying them together, dividing by this, and rehydrating the decimal, gives you 1 for the final residual. So yes, that works, but it takes an awful lot of work to get there. Now, if you did Google this solution, you might have found that there was actually a non-calculator way to demonstrate that 1093 worked. It didn't actually explain how the various numbers came about, but there was a non-calculator explanation of it. So I'm going to go through what I reckon would have been the evolution of that, which would be this. First of all, instead of forming a binary decomposition of that, what if we just find the prime factorization of 1092? So there it is, 2 times 2 times 3 times 7 times 13. So you could do this by raising powers of 2. For instance, I could have 2 to the power 13, raised to the 7, raised to the 3, and so on. That would produce the number 1092. Now it's just a case of which of these are most fortuitous to start with. I might not want to do squarings, I might combine them, do a power 6, a power 7, a power 23, a power 26, and so on. Another thing that would be handy would be if you could find some starting number, preferably that had one of these powers, that had a number close to 1, just a single digit residue. Another way you could do that would be just to stick with trying to get a single digit or a small residue, would be to have numbers as multiples of p plus a number. Because after all, if I just call p equal to the 1093 just now, the residues have to be some number. P's got to be less than, oh, that was meant to be r, not p, r for residue, and p squared. Or if you want to use the negative ones, greater than the negative of p squared. I'd want a power of 2 that doesn't necessarily get close to this. The easier problem gets close to this, so it's a multiple of that, plus a small number, or minus a small number. And when you go through them, well, to get to 1000, that's power 10. 2 to the power 10. If you go beyond that, just try the next couple above it, you eventually find that if you're at 2 to the power 14, I know I'm using a calculator here, but that's the only time, 2 to the power 14, I've got 16384. If I was to divide it by 1093, or just take some off of it, that's 14.9899. It's pretty close to a multiple of that. Now I could either have 14 lots of p plus an awful lot, or better than that, 15 lots of p minus a certain amount, and when you find the residual there, it turns out to be minus 11. Now that's quite a handy starting point for this technique. Now the 14 means I've used the 2 and the 7 so far, if that's what I'm going to stick with. But I could aim, I don't want a power 13 at the end, I could aim for 26 by doing this. If I square this side, I'll get 2 to the power 28. If I square this side, and this is where it starts to get handy having this p, squaring that would be square the first, which is a term in p squared, so obviously that's congruent to 0, twice the product, so 11 times 30 would be 330, but negative 330p, square the last, plus 121. That's still within range. Now that 28 could be my 2 times 2 times 7, and then I would just have to cube this and then raise it to power 13, but already I don't fancy doing that, because cubing that is going to give me a horrible big number at the end, and I'm trying to avoid big numbers. And it's the same with power 13. What would be handy is if I could reduce that, because it's already too big, and a 28, I could knock that down to a 26 if I divide by 4. If only they divided by 4. And this is where the wee sort of twist comes in. I could make that divide by 4 if I multiply both sides of this by a certain number. Now what could that be? Well, 121 times 10 would just go over that. We'll put 121 times 9. I really want to get close to this so I can reduce the size of that number. Well, 9 times it is 1089, which is only 4 away from there. So if I did that, if I did 9 times this side, 9 times 2 to the power 28 would be negative, now 9 times that would be 2970p plus 1089. Bringing that down, That's 4 short of that, so there's a minus 4. That gives me an extra lot of p to add on to this, so it drops that down to negative 2969p. Now, will this divide by 4? That divides by 4, but that doesn't. But this is still big enough to add one of them onto, so adding one lot of p onto this would make that negative 1876p minus 4 for 9 times 2 to the 28. Now I can divide both by 4 and get 2 of these bits, get my 2 and my 13. So 9 times 2 to the power 26 is congruent to, dividing them both by 4 gives me minus 469p minus 1. Now minus 1 is great for doing powers afterwards. Now this 9's actually 3 squared, because I don't want that there. I don't actually want these p's here. Now 3 squared is 9, obviously. I'm going to be using powers 2, 3 and 7, probably 6s and 7s. Ideally, this is going to have to be raised to one of those powers. Ideally, I'd like to be able to express that the same way as this and have something that would involve this. Well, trying the 7, just in case of trying the 6, trying the 7. Trying the 7 gives you 4782969. And when you divide that by p, you find that's congruent to 4376p plus 1. That's brilliant. That's still too big. You can take some away. That, in fact, that's a great wee number, 3 to the 14, because it turns into 4p plus 1. So since 3 to the 14 was so nice, I'll go for my power 7. So I'll raise both sides to the power 7. So I'll have 3 to the 2, well, I'll just put it in here. Raise that to the 7, raise that to the 7. So that gives me 3 to the 14 times 2 to the power, and now that's gone up to 26. I'll just leave it as 26 times 7. And this side will be, now since it's a binomial, all the terms on this side will be p squares and higher. They'll all be congruent to 0. So the last 2 terms would be 7 lots of this, negative 469p to the power 1 times negative 1 to the power 6 plus negative 1 to the power 7. Well, that's minus 1. And this part here, 7 times that is negative 3283p. Bring that back into range by adding on 1093s. And it turns, you get up to negative 4p when you do that, minus 1. That was 2 to the power 26 times 7. And then this is where this is handy, because 3 to the 14 was in fact 4p plus 1. And that side is negative of that, which means that 2 to the 26 times 7 is congruent to negative 1. Now what have I done? I've done my 2 times 13, I've done my 7, I'm just left with power 6. Raising that to power 6 will produce 2 to the 1092, and negative 1 to the power 6 is 1. There we go. So here are the only 2 values that have been found so far. Again, this was meant to be a puzzle, so it wasn't really a case for using a computer with some fancy programming. It should really just have been paper and pencil. Computers do have their place, but not in the respect of puzzles and mathematical challenges and Olympiads and so on. They should all just be strictly paper and pencil. Of course, computers have got their place in finding the gazillionth term of pi or some faraway exotic prime, because there's so many of them. But not here. Wee bit naughty. If there's anyone that has a physical proximity to Chris, should maybe give him a wee bit of a slap about for this one.